Okay, so just reviewing these, which of these is an alcohol? Remember that the formula of an alcohol is ROH, so this is the alcohol. None of these other ones have that. Looks like most of you got that one correct. This one looks like it's a bit of a range of people. But again, remember when you have an alcohol in a ring, then this becomes carbon number one. And so you get one, two, three, four dimethyl cyclohexanol. Says toughest question. So remember your start numbering with the OH group. Hang on a second. I got to turn my volume back up. What was that?
What makes it like DE instead of DI?
Oh, I'm sorry. That's a typo.
Oh, okay, okay.
Oh,
Because I was
okay.
confused.
I didn't even notice that. Thanks for catching that. I'll have to fix that. Yeah, a couple people said phenol. I kind of did that on purpose to really check you guys. Remember, for it to be a phenol, this has to be a benzene ring. So there has to be alternating double bonds in here. So that was a little bit of a tricky one there for you. Uh, Darn it. Typo. Gets me every time. Name this. Most of you got this one right. It's 2,4-pentane diol. You've got two hydroxy groups, so that makes it a diol instead of just an all. Um, and so, any questions there? What types of isomers are these? These are structural isomers because the structures actually change. You got four carbons in a row with the alcohol on the end. And then here you've got one of the carbons outside the chain. And so that's what makes this structural. If it was positional, it would just be the OH changing which carbon it was on, but the structure stays the same. Um, and stereo, you've got to have double bonds for. So you don't have any double bonds in there. What is the product of this reaction? Again, remember we substitute across that double bond. This pi bond here is going to pop, and you're going to put a hydrogen on one side and an OH on the other. So that gives you cyclohexanol. Hexanol, there's no cyclo here. The ring is still in place, so you need a cyclo in there. And I kind of did that one on purpose just to make you guys think about the ring in there. So I could see why some people would think of that, but it doesn't break the whole ring apart. Everybody got that one right. Good. Hydrogen bonding causes compounds to boil at higher temperatures because it's holding them together, so it takes more energy to get them to turn into gas. Dehydration of alcohol causes alkenes. So again, remember dehydration, you're losing water. So you're going to take an OH group off and you're going to take a hydrogen off. That's your H2O. And so you'll get that double bond forming and you'll be back to an alkene again. Any questions there? You want me to draw that? Oh, sorry, Michelle. I ended a little too soon. By the major product according to Zaitsev's rule, You guys are about 50-50 on this one. Again, you're going to get the one. Zaitsev says that it will be the one with the greater alkyl groups. And so 2,2-dimethyl-2-butene, or 2,3. Yeah, because this one here has got 1, 2, 3 alkyl groups, but this has 1, 2, 3, 4. So the reaction's going to favor this one here. Any questions there? Name this compound. So again, you're going to start with the OH here. So that's 1, 2 bromo, 3, 4 methyl phenol. Now, this case, it is a phenol because you've got the double bonds in there. You've got the benzene ring with the OH. And so for it to be 1 bromo 3 methyl, you'd have to start. Oh, I see. People started counting here and went around. Yeah, that's how I was testing that. That you always start with the OH group. So something to keep in mind. Oh, I didn't have a question in here. How do you like that? Most of you got this right. It's 2-ethoxybutane. So the precedence here, you've got 1, 2, 3, 4. That's your longest chain. And here you got 1, 2. So this becomes the functional group ethoxy. This is your butane. And this is on the second carbon in, so that gives you 2-ethoxybutane. And it wouldn't be methoxy because you do have 2 carbons here. What is a heterocyclic compound? It has an atom in the ring other than a carbon or a hydrogen. That's what a heterocyclic compound is. So if you've got an oxygen in the ring or a nitrogen in the ring itself, then that's what makes it heterocyclic. Name this compound. Good number of you got it right. So it's 1, 2, 3, 4. So it's a butane. You're going to start numbering at this end. So it's 1 butane thiol. And then that means you've got 1, 2, 3 is this methyl group. 3 methyl 1 butane thiol. And it's a
Wait, can you explain that one more time?
Yeah, so this is called a thiol because it has a sulfur instead of an oxygen, right? If you made this an oxygen, it would be an alcohol, right? So it would have the ending -ol. But when we substitute it with a sulfur, it becomes a thiol. You've got 1, 2, 3, 4 is your longest chain. So that gives you butane thiol. It's 1 butane thiol because this is on the very first carbon there. And then now you start numbering again from that functional group. So it's 1, 2, 3. So this is going to be 3 methyl 1 butane thiol. We don't use the word sulfo anywhere like that. Isopropyl thiol. I thought somebody might see this and think isopropyl or something. And 2 methyl maybe started counting from this end. I'm not sure. But again, you start with that primary functional group. Did that answer your question? Okay. Ooh, look how tiny that is. Sorry about that, guys. I didn't realize how small it was. What is the missing product? So we're reacting an alcohol with a halogenated phosphorus compound, and you're going to get phosphoric acid off, and you're going to get something else, and that's going to be bromobutane, because this bromine is going to go in and replace this OH group. And since it's on the second carbon, then that'll be 2-bromobutane. The phosphorus doesn't go on it, so it can't be that. It's in the second position, so it wouldn't be 4. 4 in this case would have to be on the end, which would make it 1, actually. Right? So you can't really have 4 on that. Some of you thought that it would put 2 bromines on there, but that's not the case. That says this is the one people spent the most time on. I'm assuming that's what they mean there. So go back and review that stuff. Okay, that covers our review. Let's see, it's 6:39. Why don't we start with chapter 4, and then we'll take our break. Go into the slideshow. So tonight, chapter 4 is aldehydes and ketones. And we're going to just start with aldehydes. So this is what's called a carbonyl group. It's a carbon with a double bond with an oxygen on it. So just like the OH is a hydroxy group, the C double bond O is called a carbonyl group. An aldehyde is a carbonyl containing organic compound with at least one hydrogen attached to the carbon. And notice it says at least one. So here, this is the smallest aldehyde you can have with just one carbon in it. This is actually formaldehyde. And you see here that there's 2 hydrogens attached to it. But that's fine because it has to be at least 1. So this C double bond OH is that tells you that this is an aldehyde. Up here we got a 3-carbon chain, but you've got a hydrogen attached here to this double bond O, so this is an aldehyde functional group as well. So this is a 3-carbon ring aldehyde. And it could be with a ring as well. Remember, this is my little quickie abbreviation for benzene. So this is a benzene ring, but it's got a carbon with a double bond O and 1 hydrogen. So this is an aldehyde as well. This is benzaldehyde. The general formula that people use for this is RCHO. So this tells you that there's some chain, but you've got a carbon with a hydrogen and a double bond oxygen. Oh, Anna asks, is the test this coming weekend? No, if you go back, I revised the syllabus. I want to make sure that we cover both chapters and do a review of the chapter before you take the test. So the exam 2 is not this weekend, it's next weekend. And you can't have cyclic aldehydes because you'd end up with 5 bonds. You look at this carbon right here. You can't have a double bond oxygen and have a hydrogen. Remember, it's got to have both of these. So for it to have both, you'd have to have one bond here, another bond over there to that carbon, a bond to this hydrogen, and then 2 bonds to the oxygen, which gives you 5. And carbon can't have 5 bonds, it can only have 4. So you can't have cyclic aldehydes. So naming rules of aldehydes. You select the longest chain that has the carbon of the carbonyl group. Just kind of like we've been doing with all of our other naming. You name the parent chain by changing the ending to al. So if you remember, alcohol was all, O-L, now it's al, A-L. You number the parent chain starting at the carbonyl carbon atom. You determine other functional groups and locations. And benzene rings are called benzaldehydes, is their base name. So that is one kind of an exception. So if we look at this, here we have pentanal. So we've got 5 carbons across here. You do have the C double bond OH, so this is an aldehyde. You start numbering here. So this is pentanal or 1-pentanal. Here you've got a hydroxy group on this, but again, remember that you start counting at this end. So this becomes 3-hydroxypentanal. And this oxygen, or I'm sorry, this hydroxy group is on that 3rd carbon in that chain. And then here we have our benzene ring. The circle in the middle is denoting benzene. We're going to start numbering on this carbonyl group here. So, and then you alphabetize like normal. So you're going to go 3-chloral for 5-methyl benzaldehyde. And then down here we've got 1, 2, 3, 4 carbons. We've got a methyl group hanging off here. Here is our aldehyde group. So this is going to be butanal, and this is on the 3rd carbon, so that's going to be 3-methyl butanal. Any questions on any of those examples at all? Nope. You can have dialdehydes. So you can see here that there's a C double bond OH on this end of the chain and a C double bond OH on this end. And this has 5 carbons in it, so this would be called pentane dial. Oops, not diol, but dial. And the same here as butane dial. So they're on the ends. So you can do that. Be very aware of this. You know, don't let diol trip you up. Diol has got 2 OH groups on it, not 2 aldehyde groups on it. Any questions there? Okay, so here's a practice problem. This is an aldehyde. Go ahead and give this a name. Just type it in when you're done. Okay, we got a couple in. Any others? All right, looks like we're building a consensus. And yes, you guys are right. So we've got 1, 2, 3, 4 carbons. So it's a butanal. And you start numbering here. So this is 2 and 3. So this would be 2, 3 dibromobutanal. Try that one there.
Dichloro 2.
Drew, do you know you're unmuted?
Oh no.
It's
That's my
okay,
bad.
but I thought I'd let you know in case you didn't want to be unmuted. Okay, we got 1 in. Any others? Anybody else? We have some differences of opinion. That is my final answer. I like it. All right, let's see what we get here. So we have 3,4-dichloryl 6-propylbenzaldehyde. So this whole critter right here is your benzaldehyde. We're going to start counting here. You've got this propyl group off of here. 1, 2, 3. And you got 2 chlorines. Chlorines come first alphabetically. So you're going to go 1, 2, 3, 4. So 3,4-dichloryl 5,6 propylbenzaldehyde.
So do we always start the count on the OCH chain?
You always started on this, the functional group, yes.
Okay, thank you.
Just like you do with alcohols, you always start with the OH on the ring. You're going to start here on the ring as well.
Question. Why wouldn't we go to the right and like name the propyl group first, just because it comes like second, like a lower number?
It's
Do you
not-
always do alphabetical before numbering?
You always do alphabetical, right? So you
Okay.
want to get the chloral first.
Okay, thank you.
Any other questions here? All right.
This might be a stupid question because you probably have already answered it, but the OCH, that's the benzaldehyde, right?
No, this whole thing is.
Okay.
So a benzene ring with this carbonyl group on it is called benzaldehyde. It gets all lumped together.
Thank you so much.
It's never a stupid question. I think you say that every time. I'll
Yeah.
break you of it eventually. Okay, good. So you can have positional isomers within aldehydes. Here, both of these compounds, we've got 3-chlorobutanol and 2-chlorobutanol. It's just where the chlorine is at. So these are positional isomers of each other. In this particular case, they both have the same formula, C4H7ClO. So these are isomers of one another. And you can also have structural isomers or skeletal isomers as well. So here, both of these are C4H8O. We've got butanal, so we've got 1, 2, 3, 4 carbons in the chain, and so this is butanal. And then here we've got only 3 in the chain, and 1 is now a functional group off of that chain, and so this gives us 2-methylpropanal. But these are isomers of one another because they have the exact same molecular formula.
Just so I'm clear, because you always have to have the OCH group at the end of like a chain, if that's the only thing, you do not have to number it, correct?
Right. Yeah, this
Okay.
you could call this 1-butanal, or you could just call it butanal.
Okay.
Okay, well, this is probably a good place to take a break. So let's go ahead.
Can I ask a quick question? I'm sorry.
Yep, no problem.
For the last one, the skeletal structure, I'm not seeing the 8 hydrogen.
So you've got 1, 2, 3, 4, 5, 6, 7, 8.
Oh, okay. I was counting. Okay. Never mind.
I
I
did-
see what I did wrong.
I didn't draw the H's in there. I got lazy.
That's fine. Yeah. Thank you.
Sure thing. Okay, it's 5-2, 4-2. So why don't we come back at 10 after? I'm going to pause recording here before I forget. I've also been going without my dot. There we go. I need to share again. There's so many different things I got to click on here. All right, you guys see on my screen? We're good?
Yes.
I'm
Yeah.
recording. Okay.
Yes.
All right, so ketones. So ketones are a carbonyl containing organic compound where the carbon has 2 other carbons attached to it. So instead of that hydrogen, it's got to have, so if you remember, an aldehyde was RCOH. So this is going to be RCOR. So here we have a situation where we've got a carbon, 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 carbon. This carbon here has got 4 bonds. One's to this carbon, one's to that carbon, and then you got the double bond to the oxygen. So that makes this a ketone. And here we've got two benzene rings with a double bond to the oxygen. And so again, this is still RCOR. The R's just happen to be benzene rings. So that's a ketone as well. You can have cyclic ketones because this carbon here has 4 bonds. There's no hydrogen there. So it's got 1 carbon here, 1 carbon there, and then 2 bonds to the oxygen. So this is a ketone. The same case over here, we've got a 5-membered ring. You can have a double bond to an oxygen on that carbon, because this carbon again still only has 4. It's got 1 with that carbon, 1 with this carbon, and then 2 with the oxygen. In this case, this carbon here's got a methyl group off of it, and this one over here is a methyl group off of it, but this is still a cyclic ketone. And then you can actually have benzene with double bond oxygens on either side. That's also a ketone. I don't know why I put that example in, but it's there. So naming rules. Select the largest chain containing the carbon, the carbonyl group. Sounds similar, doesn't it? The parent chain ending is -one. Instead of -al, you have -one for ketone. You number the chain such that the carbon in the carbonyl group has the lowest number. Determine the name and location of the other functional groups. Cyclic ketones have the carbon in the carbonyl group numbered as number 1. So pretty much the same thing over and over again. So here we have 2-pentanone. We've got 1, 2, 3, 4, 5 carbons. So that gives us pentanone. And this carbonyl carbon is the second one in the chain. So that's 2-pentanone. Here we have a ring with a carbonyl group here and a methyl group here. So this is going to be number 1 with the carbonyl carbon, and that makes this 2. So you get 2-methyl cyclohexanone. And here we've got a 5-member chain again. 1, 2, 3, 4, 5 is the longest chain we can make that has the carbonyl group in the chain. So that gives us pentanone. This is on the second carbon, so that's 2-pentanone. And then that means this is the third carbon, so it's 3-methyl 2-pentanone. Any
Number
questions?
closest to the ketone group. Like, so if this methyl, or we'll say the methyl or something was like actually a chloro and it was on the like 4th carbon, would we number from there, or would we number from the ketone group?
Nope, you always number closest to the ketone group. Whatever will give you the smallest number for your ketone.
Okay.
Can you show us again how you numbered that one?
This one
So-
here?
Yeah.
Okay, so you've got 1, 2, 3, 4, 5 carbons, so that's pent, right? It's a ketone, so it's -one. And then now you want this to be the smallest number you can get it. So you can go 1, 2, or you could go 1, 2, 3, 4. So you're going to go with the 2. So you're going to start numbering down here. So you're going to go 1,
Okay.
2, and then 3.
That confuses me that you count it one way and then you go backwards.
Oh, I'm sorry. I
No,
guess
no, no.
I
It's
shouldn't do
I'm just
that.
mean I don't know why it confuses me, but it does for some reason.
Okay, well,
Is-
I'll
Do
try
you
not to
recommend
that.
anything that I can remember for next time so I don't have
Uh,
a mistake?
Well, you just have to choose which one will give you the lowest amount. So, if I start over here, I get 4. If I start here, I get 2. So you're going to start here.
Okay,
Does that answer your question? I'm not sure if it does
Yes.
or not.
thank you.
I think I was throwing you because I was counting like this, right? And then came
Yes.
back and changed it. Yeah,
Yes.
I'll try not to do that.
Okay, thank you.
So, yeah, I can see how that can be a little confusing. By the way, I think that the 7th edition may give different names for this. I'm going to look at that this week. But I was looking at it during the break, and this is the naming convention, but it may have changed, so I'll double check that. And you can have diketones as well, just like we have diols and dials. You can have diones, so it just becomes a dione. So here we have 1, 2, 3, 4, 5 carbons, so that's our pent. You've got 2 carbonyl groups with these carbons are both attached to other carbons, right? So that makes these ketones. And so that's a dione. And then in this particular case, it doesn't matter which side you start on. It's 1, 2, 3, 4. So you get 2,4 pentane dione. In this example, it is going to matter. You're going to want to count as closest to one of your carbonyl groups as you can. So here it's going to be 1, 2, 3. So that gives us 2,3-hexane dione. If you start on this side, you'd end up with 1, 2, 3, 4, 5. You'd end up with 4 or 5 hexane dione. 2, 3 is lower, so you want to start on this side. Any questions there? So try to name this guy. Can I call you back in a bit? I'm in class. All right. Talk to you a bit. Bye. Yeah, Andrew, we're going to talk about that in a minute. But if you're okay, it looks like we have a consensus here. So yeah, we have 3 bromo, 2 octanone. So you're going to start on this side because that's closest to this carbonyl group. So you've got 1, 2, 3 bromo, and then this is on the second carbon, so that's going to be 2 octanone. Good.
So do we end the octanone? Is it octa and then none? Or I was confused about that. Because some people said octon and some people like OCTONE, and then others said OCTANONE.
Yeah, no,
What's the difference?
yeah, it's pentanone, hexanone, octanone. So it's just, you got your octa, hexa, whatever your 3-1 is. Did that answer your question?
So we don't use it's not, yes, it answered my question, sorry.
Are you asking if it's octane-one? Is that what you're asking?
Well, I was confused because when I was looking at the rules, it said to add ONE at the end. So I was just wondering where people were getting the other like N. So is it like octane and instead of an E you add ONE?
Yeah, yeah.
Okay, that's what I was confused on. Sorry.
No, that's good clarification. I maybe need to go back and make those rules a little bit more specific. Okay, this one, try to draw this one out. So 3-bromocyclopentanone. And just tell me when you're done since you can't draw it on the screen. While you're doing that, I'm going to double check something here. Yeah, I definitely see a difference between 4th edition, 7th edition here. So when you do some of your problems, I'll have to point this out to you guys so that when you do your problems, you're not thrown. Using 2 different books. Pain. Okay, everybody pretty much done. So did you come up with something like this? So it's a cyclopentanone, so that means you're going to have a ring with 5 carbons in it. You're always going to start numbering here with that carbonyl carbon. And then you want to get lowest number, so that'll be 1, 2, 3 bromocyclopentanone. Any questions there? Okay, ketones can also have isomers, positional isomers. So again, it's where the carbonyl group is at. This is 2-pentanone because it's on the 2nd carbon. And this is 3-pentanone. It's on the 3rd carbon. So these two have the exact same molecular formula, and therefore they are positional isomers. The structure is not different. It's just that the position of the carbonyl group is shifted. You can also have skeletal isomers. Both of these compounds have the molecular formula C7H14O. Here we have 2-heptanone. You've got 1, 2, 3, 4, 5, 6, 7. So that's our heptanone. And it's on the 2nd carbon, so it's 2-heptanone. And over here, it's the same number of carbons, it's just the skeleton's been rearranged and we got 2 methyl groups here. What in the world is going on? People are texting like mad. Silence my phone. Okay. So we have here, again, we want to start numbering closest to this carbonyl group. So this is going to be 1, 2-pentanone because we've got 1, 2, 3, 4, 5. And so this is going to be 2-pentanone. And then that means that this is the third carbon and this is the fourth one. So we've got 4,4-dimethyl 2-pentanone. Any questions there? So these two are isomers of one another. They're skeletal or structural isomers. Aldehydes and ketones can also be isomers of each other. So both propanal and propanone have the same molecular formula, C3H6O. And so these two are isomers, even though one is an aldehyde. It's got a hydrogen here. So this is an aldehyde, and this has got an R group here and an R group here. This is a ketone, but they are isomers of one another. Any questions there? Okay, Andrew asked the question, what if you have mixed functional groups? So what if you have, so here we have an aldehyde group, but we also have a ketone group here. This is RCOR. So which is it? Well, they had to come up with a naming convention for this. So there's a priority. The lowest priority are alkoxy groups, alkyl groups, and halogen groups. The next highest is alkynes. So if you have a triple bond, then it's going to be called an alkyne, even though it has a halogen in it. If it's got both a triple bond and a double bond, it will be an alkene. Even though it has a triple bond in there, alkene takes priority over alkyne. And if it's got an alcohol, then it's going to trump all of these. So if there's an alcohol group, but there's a triple bond, it's still an alcohol. And if it's got a double bond, but it has a OH group, it's still an alcohol. And they get named differently. And then ketones trump alcohols and aldehydes trump ketones. Any questions there? Does that make sense what we're doing? I'll assume silence is golden. So here we have an example of an aldehyde and a ketone in the same molecule. Like I said, you've got RCOR. So this is a ketone, but I also have an RCOH. This is also an aldehyde. Since aldehyde trumps ketone, it's going to be called an aldehyde. So you look at that portion of it, and you call that, in this case, ethanal, because there's 2 carbons in there. This becomes a functional group off of that aldehyde. So this becomes 2-methoxyethanal. Did I explain the 3-bromocyclopentanone question? Where was that at? This one here? What's your question around that? How do we know where the double bond O goes? You just know that this has to be number 1. And since I gave you that it's 3-bromo, then you know the bromine has to be 1 away from this one, right? So it's,
Yeah, I was just confused because you asked us to draw it. So I was just wondering, does it matter where we start that? Like when we draw the picture?
Does it matter where you start it? Where you start drawing it?
So you asked us to draw that one. It doesn't matter where we put the O double bond?
No. No, it does not. That's
Okay,
a good question,
then,
actually. Very good
and
question. And actually, it doesn't matter where you put the bromine as long as it's in the 3rd position. So you could put it here.
Okay, that's what I was wondering.
You count this way, You could be 3 bromo still here. Yeah,
you.
absolutely. Good question. Good question. Okay, so this becomes a methoxy functional group off of this aldehyde. Any questions there?
I just have a quick question on this one. Oh, yeah. So the first was ketone, and then you said since it was ethanol, it has 2 carbons, and then what did you say after that?
Yeah, so
Like on the
so you look at you say aldehyde trumps ketone. So I'm going to make this ketone group a functional group. So I look at everything up to this carbonyl group here, and that becomes your aldehyde. Since there's 2 carbons here, this is going to be ethanal. And then you got to name this guy. There's only 1 carbon with this carbonyl group. So this is going to be called methoxy. If you go back and look at last week's lecture, you see that 1 carbon with a COO is called a methoxy. If there was 2 carbons out here, it'd be ethoxy, so forth and so on. And so this is methoxy. And since it's on the second carbon of this aldehyde, then it's going to be 2-methoxy. Does that make sense?
I got it. Thank you. Yep.
That'll contort your brain, won't it? Now here we have an aldehyde alcohol. If we go back to our chart, aldehyde's at the top, so it's going to trump the alcohol. So that means this becomes a functional group rather than the primary name. So again, you're going to take the longest chain that you can. In this case, it's going to have 3 carbons in it, so that gives you propanal. And then this is the 3rd carbon, so this will be 3-hydroxypropanal. Any questions there? In the case of an alcohol alkene, alcohol is going to trump an alkene. So in this case, we've got an OH group, and we also have a double bond, but this is going to be an alcohol. So that means we look at our longest chain again. We've got 1, 2, 3, 4, 5. So it's going to be a pentanol. But you got to address this double bond here, right? And so how that's done, according to the 4th edition book, is this is 4-pentanol. This E here is like pentene, and you're dropping the E off the end and sticking the OL on the end there. And so this becomes 4, because it's on the double bonds on this 4th carbon. It becomes 4-pentanol, not pentanol. That would be without a double bond there. The 7th edition actually calls this 4-pentan-1-ol. And so if you see this in the problems, I just didn't want this to throw you. So the 1-ol is indicating that this alcohol is on the 1st carbon. And then the pentan is telling you that there's a double bond in this 5-carbon chain, and it's on the 4th carbon. The test will be using this nomenclature, but I wanted you to be aware of this since since most of you are using the 7th edition and you're doing the problems, I didn't want that throwing you with that. This is where I think I just need to go 7th edition. We'll drop this all together, and this is the newer naming convention, and the chemists should quit changing their rules. This is what I learned, 40 years ago, but it's changed in recent years, apparently. Any questions there? Okay, physical properties of aldehydes and ketones. So,
There was
boy,
a question in the chat, Professor.
oh, I'm sorry. Is the name methoxy used for both ketones and ethers? They have different connectives. They have different connectives. This is treated at, we had this with ethers, right, where it was ROR. I'm not sure what you mean by different connectors. Can you maybe elaborate?
Yeah, and ketones they have a carbonyl group, and in ethers they don't. So I don't know if there's something name wise difference.
Oh, as far, you mean because it's a double bond or a single bond here?
Yeah, so I know with ethers they have it's like a CH group, an O, and then CH group. This one has a CH group which is double bonded to an O. That makes sense.
Yeah. Yeah, it gets used as the same name. I'll go back and double check that, but I'm pretty sure that's the case. Let me look here real quick. Yeah, so with an ether, it would be methoxy as the functional group because it's just CH3O is what you're saying. And then let's look at our combination ones. Just double checking here. Nomenclature for ketones. This may not be in the book. I'm not seeing it. I must have got this from another book or something. Unless it's later. Oh. All right. Well, I got two things to check out, I guess. Where's their little... I know he's got the priority chart in here. But I'm not seeing it as well. All right, so I need to jot these down and check them out for you guys. So one is methoxy with R-C-double-O-R. And then the other one was numbering by lowest number or alphabetical. All right, I'll double check both of those to let you guys know. Okay, so boiling point here of compounds of similar mass, alkanes will have the lowest boiling point. Aldehydes and ketones will be higher than alkanes, and alcohols will have the highest. And the reason for this is that you do have a dipole moment here on these carbonyl groups. So you're going to have a partial negative and a partial positive on the carbon, partial negative on the oxygen. So there will be these dipole attractions. But aldehydes and ketones don't do hydrogen bonding. So alcohols, if you remember, we've got methanol here. You get bonding with this oxygen and other hydrogens within the solution, and so that's going to have a stronger bonding effect than just these dipole-dipole moments. And so that's why they're lower than alcohols. And both of these are higher than alkanes because alkanes don't have either one of these. Make sense? All right, solubility. Hydrogen bonding does cause for lower mass aldehydes and ketones to be water soluble, but only smaller aldehydes and ketones will be water soluble. All of the aldehydes and ketones will be soluble in organic nonpolar solvents. All right, chemical reactions. So you can oxidize an alcohol. If you oxidize, I think we looked at this last week as well. If you have a primary alcohol here, so this OH is on a carbon that is only connected to one other chain of carbons, there's two oxygens here, then this gets oxidized into an aldehyde. So you're going to lose one of the hydrogens, and you're going to lose the other hydrogen that's on the oxygen here and form a double bond. You'll get hydrogen gas off as a byproduct, and you now have an aldehyde because you've got a C double bond OH. But if you oxidize a secondary, so here is a carbon that's attached to two R groups, then again, you're going to lose the two hydrogens and form a double bond, and you now have RCOR, you have a ketone. So primary alcohols give you aldehydes, secondary alcohols give you ketones. Any questions there? If you oxidize an aldehyde, so here we have an aldehyde, RCOH. If you oxidize that, you're going to add an oxygen into this compound, and you're going to get RCOOH, which is called a carboxylic acid. And I believe the next chapter we'll be talking about carboxylic acids in more detail. Ketones do not oxidize readily, so we don't have to worry about those. This is used, by the way, in this oxidation and glucose testing. So hydrogen peroxide has a reaction. So H2O2 is hydrogen peroxide. It will react with a dye that's equivalent to how much of this glucose is in your bloodstream. And so what they do is they're not actually measuring the glucose itself. They're actually measuring how much peroxide or hydrogen peroxide you get out of this oxidation reaction. So we're going to take glucose, we're going to oxidize it in the presence of water with an enzyme. Remember, I don't know if we've talked about this or not, but an enzyme's like a catalyst. It isn't consumed in the process, but it aids the reaction. And you're going to convert this guy into a carboxylic acid. So you're getting this, the RCOOH on the end here. But you're going to form hydrogen peroxide in the concentration equivalent of what the glucose was. So this is 1 mole of this you're going to get 1 mole of this. So they react this with a dye and they can measure your blood glucose concentration. So again, since most of you are going medical, I thought I'd give you this real world example of that. We can also reduce these guys. If you reduce an aldehyde, you're just going to reverse the process and you're going to end up with a primary alcohol. And if you reduce a ketone, you're going to end up with a secondary alcohol. So this one is going to, you're going to add a hydrogen onto here and an hydrogen here. So it's just reversing what we saw a moment ago. And the same here. So by adding those on there, you're going to end up with a primary alcohol and a secondary alcohol. Any questions there? Okay. So what forms when this alcohol is oxidized? Give me the name of the resulting product. Okay, got a few answers coming in. Okay, people are saying propanal, and that's correct. So we're going to end up forming a double bond with this O, with this oxygen here, and so this is going to be an aldehyde, and we have propanal. I did find my spot here, Andrew, in the 7th edition book. If you look on page no, I lost it. I was just looking at it. Where did it go? Here it is. If you look at page 471 in the book, it gives you that priority that I explained to you guys. And then they give you an example. That's all he does, though. He doesn't do much, where they call it methoxyethanol and hydroxypropanol. So apparently they're using the same term. .
Wait, why is it propanol?
I'm just saying the book. There's an example. Not here. Oh, propanol here. I'm sorry. I'm
Yeah.
doing two things at once. You've got 1, 2, 3 carbons, so that's going to be prop, and then it's enal because it's an aldehyde.
Oh, got it. Thank you.
Oh, but I see in the book. Actually, I do have an error here, Andrew. In the book, there's single bonds, not double bonds. Okay, I'll have to look into that and get back to you guys. Yeah, I actually have that wrong. If you go over onto page 473, that's funny. The other semesters, nobody ever said anything about this. So you're smarter than the other classes. If you look on 473, it's called 4-oxopentanal. So I think I've got that wrong in my slide. Thank you for catching that. Let me go to I'm going to jump over here. Yeah, so they give an example in the book. I think I can make this larger. So here's a case where we have an aldehyde and also a ketone. And I gave you the name wrong because what they're doing is they're calling this a pentanal with an oxo group. The double bond is on this 4th carbon here. So I need to revise that slide and fix that. Sorry about that. I'll need to look at my test to make sure I didn't get that wrong there too.
So for this most recent problem, when it's in a L, I'm probably gonna say it wrong. When it's in a L, I can't say it. What we were just talking about, does that make it a null when it's in an aldehyde or whatever it is? Sorry. Like the H and the OH, you said that's an aldehyde. Is that why it is NaL?
Yeah, this would be propanol, OL, because it's an alcohol, right? But when we oxidize it, it becomes an aldehyde, so it becomes propanal. This is an aldehyde because this is C double bond OH, whereas this is a COH, so this is going to be propanol. Is that what
Got
you're
it, thank
asking?
you.
Yeah, and this becomes a aldehyde. All right, what do we form when we oxidize this alcohol? Okay, I've got a couple answers in. Anybody else? Any others? Okay, we do have cyclohexanone. So again, you're going to lose this hydrogen here and it's going to form a double bond. And so you're going to get cyclohexanone. And you could say one cyclohexanone, but it doesn't matter because it could be anywhere on this ring.
So if that O double bond had an H with it, like the previous problem, would that then make it cyclohexanol?
If it had an H out here,
Like
or
the
you-
problem before, how that carbon, if that carbon had an H on it, is that what would make it a propan, like a cyclohexanol?
well, remember you can only have 4 bonds here, so you've got 1, 2, 3, 4. So this carbon can't have a hydrogen. And so this can't be an aldehyde.
Got it. Thank you.
Any other questions? Okay, there is a critter called a hemiacetal. Oops. This is a carbon that has both a hydroxy group and an alkoxy group on it. So this carbon here, it can either have hydrogens or R chains here, but it has a hydroxy group on this carbon, and it also has an alkoxy group on this. And this is called a hemiacetal. Hemi means half, and you'll see why in a minute this is a half of an acetal. You might be able to guess. Hemiacetals and acetals become very important in the chemistry in the body. So this is why we're bringing this up. We will see these more again. So here we have an aldehyde. You've got RCOH, and we're going to react it with a alcohol, and this will form a hemiacetal. So you're going to have this R1, and this carbon is going to be right here. That double bond is going to pop, and you're going to put a hydrogen there, and then this OR here is going to connect into that carbon. And so now you're going to get this RCOHOR, and that is therefore a hemiacetal. Any questions there? I should have drawn these in different colors like I did some of the other ones.
It would be helpful for me if you could maybe draw where the R2 is going, where the double bond is breaking and kind of connecting to new things, stuff like that.
Yeah, so
Does that
if
make
we,
sense?
yeah.
Yeah, or where you can I don't know, I wish I could almost do it on my screen where you pull the R2 over and you're like, oh, here it's going to connect over to this oxygen.
Yep. So
thing.
what happens here is this guy here is going to pop off, right? And then you're going to take the hydrogen here is going to go onto that oxygen. And this OR now needs to bond with something, so it's going to bond in right here. And that's how you get the R1C OH and then the OR2. Does that help?
Yes, thank you.
Clear all drawings. Yeah, some of the other ones I did them in different colors. I should do that again. And then you can form hemiacetal from a ketone. So again, I guess go back to annotating here for a second. So again, when this reaction occurs, in this case, this is going to pop. This bond here is going to pop. And you're going to get the hydrogen here going onto that oxygen. And then you're going to get this OR3 connecting to that carbon. And so you're going to get two R chains on this carbon, but this carbon has an OH group and an OR group, so this is a hemiacetal. Remember, these can be H's or R's. So in the case of ketone, this would be an H here. But in the case of an aldehyde, that would be an H. But in the case of a ketone, you just end up with two R groups. Does that make sense? Okay, so is this a hemiacetal or not? What do you guys think? Okay, it looks like we're building a consensus. This is a hemiacetal because you have a carbon here with an OH. It's got an R group here, and it's got an OR group over here. So this O has got an R group connected to it. It just happens to be in a ring. And this carbon here, doesn't matter. It could be an H or an R, but in this case, it happens to be an R. It's connected over here. So this is a hemiacetal. Everybody see that? Remember our formula. It's just like this, except it's in a ring. So you could think about this as being like the ring, or yeah, all of this being the ring, I guess. And so this is a hemiacetal. Any questions there? An acetal, instead of a hemi, is where you have two OR groups attached to the same carbon. So two alkoxy groups attached to the same carbon. So a hemiacetal is an OH up here and an OR here. Of course, the position doesn't matter, but you have one of each. Here you have two ORs to the same carbon. Or you could think of this as like two ethers, right? It's kind of ROR, ROR, both ways. And you form acetals with hemiacetals. So here we have RCOH OR2, the R1 over here. If you react that with an alcohol in the presence of acid, then you're going to get a dehydration basically. You're going to pull water off and you're going to lose this hydrogen here. Here, let me draw this again. So this hydrogen is going to come off and this OH is going to come off. And that gives you your H2O over there. I don't know why I'm trying to draw this with my mouse instead of my pen. And then that leaves this portion right here. So that goes in and connects to that carbon. And so you end up with water as your byproduct. And you're going to have R1C, OR3, OR2H. And this is an acetal. This is a half an acetal because this is not an R group here. That's a hydrogen. Any questions there? We're good? If you take an acetal and you hydrate it in the presence of acid, then you're going to get out either an aldehyde or a ketone plus 2 alcohols. So you're basically going to pop these 2 off, and then you're going to end up with either depending on what these other groups are here. If this is an R, and this is an R, then this would be a ketone. If one of these is a hydrogen, then it's going to be an aldehyde. Everybody see that? And you're going to get your 2 alcohols off because you've got this R1OH is going to be your first alcohol, and this R2OH is going to be your second alcohol. So again, if these are both carbons here, then it will be a ketone. If one of these is a hydrogen, then you'll have an aldehyde. Any questions there? Okay, you guys want to take another break? It's 8:15. Let's take a 10-minute break and be back at 8:25. I guess it'll be a 12-minute break. And then we'll wrap up. Okay, I did go back and fix this slide during the break. And thank you, Andrew, for catching this. So this is, again, the aldehyde does take precedence over the ketone, but I had the name wrong. This would be 4-oxopentanal, oxo denoting the double bond with the oxygen. And you've got 1, 2, 3, 4, 1, 2, 3, 4. Oops, this should be butanal. Sorry, 1, 2, 3, 4. This should be 4-oxobutanal. Not pentanal.
3-oxobutanol.
Thank you. Boy. Well, when I screw it up good. All righty. There we go. So that's fixed in the slide for you guys. So this gets treated as the functional group, not the whole thing. I had that wrong. Okay.
So is that answer instead of the 2-methoxenol?
Methoxyethanol.
Oh yeah, that's how I say it.
Yep.
Okay, thanks.
This one's still good. that one's good as well. Okay, so we go back here now. All right. So you can polymerize aldehydes. Phenol in excess of formaldehyde will polymerize. So we've got this, remember phenol is a benzene ring with a hydroxy group off of it. It will react with formaldehyde. Formaldehyde is going to be just one carbon, a one carbon aldehyde. So this will form very long chains. You can see this continues here and continues here. It can even have cross-chain linkages with the formaldehyde and make even bigger chains. And this was the first polymer actually invented. It was given the name Bakelite, and it was used to make hard plastics, and it originally was used in the making of like cheap jewelry, plastic jewelry. And so this was done, I want to say it's either the late 40s or early 50s, but I could be wrong on that. But so you can get polymerization with formaldehyde with phenol. You can have sulfur carbonyl groups, so you've got a double bond S instead of a double bond O, and these are called thials. And if you replace the oxygen, like you have here, then it's either going to be a thioaldehyde or a thioketone, depending on whether these are hydrogens or not. If these are both carbons, then this is going to be a thioketone. If one of these is a hydrogen, then it's going to be a thioaldehyde. If you replace the carbon, then you get what's called a sulfoxide. So you can see here, we've got an R-S double bond O-R. So it's the carbon that has the sulfur, and this is called a sulfoxide. So RSOR is a sulfoxide. And this reaction happens when you take a thioether. Remember we talked about thioethers last week. You have RSR instead of ROR. And if you oxidize this, you will get a sulfoxide. Any questions there? All right, then just kind of wrap up tonight. We have a bunch of real world examples. I like giving these to you guys because, again, we live in a real world, and kind of helps you kind of see chemistry in action. So formaldehyde is the one we were just talking about. It polymerizes with phenol. Formaldehyde is going to be just one carbon. This, if you remember, we had this in another example. This form is means one carbon. It's a common name. We would call this methanal. So you've got one carbon with a double bond O and hydrogens on either side. Formaldehyde is used to preserve biological specimens. It's also used in embalming, or at least it was. I don't know if it still is. I think I actually last semester had a student in the class that had worked at a mortuary, or their family owned one or something. And I think he said that they still use it, but I'm not sure now. But how it preserves bodies is it basically it hardens the proteins so they don't break down. And this is why if you've ever touched an embalmed corpse, they feel really hard. It's because that proteins have been hardened up. made more rigid. So this is an example of an aldehyde in the real world. Benzaldehyde, so we've got this benzene ring with this aldehyde group onto it. So this is all benzaldehyde. This is responsible for almond flavor. This generates an almond flavor. Vanillin is a benzene ring that's got a OR group here, an OH group here, and an aldehyde group over here. So this gets called 4-hydroxy-3-methoxybenzaldehyde. And this is, the common name is vanillin, which is the vanilla flavor. 2,3-butadiene. So this is a diketone. We've got 1, 2, 3, 4. That's your butane. Dione, because you have 2 carbonyl groups there. And 2,3-butadiene is the flavor of butter. This is actually a compound that forms when you churn milk into butter. And it gives it that buttery flavor. 2-heptanone. So this is a ketone because we've got a carbon connected to 2 other carbons. There's no hydrogen there. This is responsible for the clove flavoring. We have here a ketone. This is 2-chloral-1-phenylethanone. You guys don't have to memorize all these or anything. I'm just giving these to you. But this is the active ingredient in tear gas or mace that is used for, subduing somebody. And when you're cutting up onions and you start crying, a lacrimator is something that causes you to cry. I forgot to say that. So propane ethiol. So you see that this is a thiol because it's a double bond S, not double bond O. And it's 3 carbons, so it's propane thiol. This is the active ingredient in onions that causes you to tear up when you're cutting the onions. So next time you're, why does it do it?
Like, why does it cause your eyes to water so bad?
It probably just irritates your eyes and your eyes water to try to, get rid of the irritant. Probably the case with both of these. So now when you're cutting onions, you can scream to your family, I'm getting a thiol, just to freak them out. Here you can see how complicated these molecules get. We're never going to name these. I'm not going to ask you to name these, but you could just see, look at this crazy name. This is the name of this. This is cortisone. Cortisone creams are used to hydrate your skin. Cortisone is actually also an active ingredient in chemistry in the body as well. And so this crazy compound is cortisone. And again, it is a ketone here. And so notice that it's actually a dione because you've got a double bond O here and a double bond O here. It's actually a trione, but this is getting treated differently somehow. But anyway, this is a ketone that's used to hydrate skin. And this is testosterone. Again, we have a ketone group over here because this carbon is attached to 2 other carbons with a double bond O. And you got an alcohol group way over here, but this is the male hormone. And Ooh, we're at the end. So I picked out problems in both 4th and 7th edition for you guys to work on and practice. And I guess we're done a little early. I'm surprised. So you guys are, well, I don't have problems prepared. So if you guys want to stay and work on problems and ask questions, you can do that, or you can take off early, whichever you want to do. But before we do that, any final questions or anything?
Thank you so much. Have a good night.
You too.
Thank you.